while we're working machine problems, it's fun to look at the machines that you see around construction sites and think about the statics that applies to those machines. Here's a picture of a skid steer and a John Deere loader. And so if you look at the skid steer, you've got obviously tire reactions here. You've got a load on this bucket. You've got the boom itself, which pivots back here. And then you have a hydraulic cylinder that lifts this boom up and down. And the question I might ask you, what is the force in the cylinder? And you look at that and you go like, oh, that looks like a hard problem. But let's work this problem. Let's just take this picture and approximate the dimensions. And so if you approximate those dimensions, so you've got the bucket out here, this member that comes down here. I'm assuming that this is about, so you can see it. I'm assuming that this is about 5 feet from here to here, from the pivot to here. This looks like about 20 degrees to me. It's probably more like 18 degrees, a little less than 20. I'm assuming that this is 15 degrees here, which probably isn't too far off. If this is 15 and 20, then this FB is 35 degrees from horizontal. And so there's a 20-degree angle between FB and this member here. I put pin reactions here at the pin. Here's my pin back here. So I put pin reactions AX and AY there. And so we want to find the force in the cylinder. And of course, we're dealing with half of this skid steer. We're not dealing with the other half. We're just dealing with this side that you see. And this 800 pound is like half of the load of this bucket and whatever its contents are. And let's let's assume that that's 3 feet from where this attaches out to there. And then this is 5 feet from here down to there. So let's find a force FB. So this is not a hard problem. So again, don't be intimidated. And notice I do this as a wireframe. I didn't draw all the details of this guy. I just basically straight lines and the pins. And so focus on a machine problem. Focus on the pins and the wires that connect those pins. Because usually these guys are dimensioned at the pins. The lines pass through these pins. And so by focusing on the pins and the wires, it gives you all of the essential information of that machine without confusing your eyes with all of the curvature and all the other stuff that goes on. So we have all the information we need. And so basically, if this is 5 feet and this is 15 degrees from horizontal, then this horizontal distance is 5 times the cosine of 15, which is 4.83 feet. So if I sum moments about A, so remember that Gini lift. If we know the angle between FB and the lift itself, then I can resolve this FB into an FB sine 20 and an FB cosine 20. And so if I sum moments about A, I have 800, and his moment arm all the way back to A is 3 plus 4.83, and then minus this guy, which is FB sine 20, his moment arm is 5. And that's equal to 0. And so my FB is 3.66 kips. That's not hard. You can do that. Once you find FB, then we could just sum forces in the X and Y for the whole problem. If we sum forces in the X direction, then I have the X component of this FB, which is 3.66 cosine of 35 minus AX. And so my AX is equal to 3 kip. And if I sum forces in the Y direction, I have FB sine 35 minus 800 plus AY is equal to 0. The AY comes up as negative 1.3 kip as drawn, which means he really should act down. And if you stop and think about it, if you sum moments about B, 800 is going to pivot counterclockwise about B. So AY has to act down to counteract that pivot. So this isn't a super hard problem once you've seen it. And so that's why we teach statics. I mean, we teach you, one of the things we teach you in statics is how to look at a real problem, to represent it with a simple representation, which is a free body diagram, and basically solve it. And to be able to think clearly about real problems. Pretty cool.